I'm gonna give up. Yep, you heard it. First thing on my to-do list today is give up on Leo. Again. Well, that shouldn't be too hard.
Haha, you think I'll actually work? Well, you've got another thing coming.
Ah! Well, that wasn't so hard. First item, done. Next item, due to actually make progress on Leo. Oh. This is gonna take a while. Cue a montage. Alright, ladies and gents, I think I have an idea. But in order to explain it, we're gonna have to do some math! Hello and welcome to Math Time. I am your host, Michael Michael Becker, and today we're going to be learning about inverse kinematic models. In robotics, inverse kinematics makes use of kinematic In robotics, inverse kinematics makes use of kinematic equations to determine joint parameters that provide desired configuration, position, and rotation for each of the robots and effectors. Thank you for tuning in, and I'll see you next time. Actually, I won't see you, but I'll see camera. Okay, that was a little stupid, but the man was right. Today we're going to be learning about inverse kinematics. So this is a lot less complicated than it sounds, but don't worry, I won't bore you with all the code. Ha! You thought I am going to bore you with all the code because I'm mean! See, here's all the code. Isn't it beautiful? Why are you asking me, Michael? Well, because I don't know what any of this means. Okay, I'll calm down a bit. Inverse kinematics sounds complicated, but it really isn't. You do it all day long without even realizing it. Just for fun, try taking an object and placing it on the table in front of you. Then try grabbing it, but only moving one joint at a time. Got it! It does not work that well. This is called forward kinematics, trying to drive an object to a certain position using only their angles. Now, just pick up the item as usual. Simple, right? What's going on is your brain knows where your hand currently is and where it needs to get to, and then it plans a path in between the two. This is called inverse kinematics, because it's not trying to move each joint one at a time in order to get to a certain position. It knows where it is because it knows the length of your limbs, so it can calculate exactly the movement you need to do. So, using mass and angles, we can figure out the end position of each of Leo's limbs. Awesome. One issue though. I feel like I say that phrase way too often. The potentiometers I use don't output angles, they output values. Check out this video for more information. So, what we need to do is convert these values that don't have a unit to angles. This should be fun. Let's do it. Ta-da! Wow, that was quick. I wish it actually took that long in order to design and build this stuff. Now I bet you're thinking, Michael, is that some 2020 extrusion mounted to a potentiometer joint and some side brackets for leveling? Why, yes it is! This handy little trinket will tell us the ratio between potentiometer values and actual angles and degrees. So what we have to do is steal our potentiometer reader from Leo, grab a couple wires, and slap the whole thing together. Brilliant! Now we can lay the whole assembly against something flat like another piece of extrusion, mark the arrow, and take down the value of the potentiometer. Then after we rotate one side, we can mark another point and record the pot value. So now let's break this down. We have a point of rotation here, and 2 marks over here. We know the distance from the rotation point to the end of the arm, and we know the distance between the 2 points. What we can do now is actually get rid of our entire setup and just replace it with an isosceles triangle. And since we know all the side lengths, that means we can use the law of cosines to get this angle, which comes out to about 17.455 degrees. And since we recorded the beginning and ending values of the potentiometer, we can see that for every 1 degree the pot turns, the value changes roughly 101.6 values. And this is all awesome and gives us a good representation of his body using math, but that doesn't include the relation of his body to the ground. I mean, just because the math is right, that doesn't mean he's standing correctly. The only way to fix this problem is to get the position and rotation of his body relative to the ground. But how do we do that without actually connecting something to the ground? Using sonar. This is an ultrasonic sensor, and basically, it's sonar. This little guy sends out a noise that we can't really hear, that shoots out, bounces off an object in front of it, and then goes back towards the sensor. What this dude does is measure the amount of time it takes to send out the sound and when it comes back, thus giving us a rough distance of how far away the object is. So if we connect 2 of these to each foot, we get 4 distances perpendicular to the foot that, if aligned horizontally, can be used to get his position relative to the ground. Awesome! Man, that was a lot to wrap my head around. Next time, we should hopefully have some mounts made for these ultrasonic sensors, and maybe even have a way to visualize the math. We should be able to see whether or not it's actually a good fit for Leo or not, but I'm really excited about this idea, and if you're excited about it too, you better subscribe so that you don't miss out on it. Anyway, I'm Michael, never be afraid to share your talents, and I'll see you next time.